As you're writing down your input today, we are going to distribute and combine like terms to simplify algebraic expressions. This should seem like a very familiar aim. This is pretty much the same aim as on Friday. And you remember I said on Friday that I thought that lesson was particularly difficult, not necessarily because there were a lot of difficult concepts, but more because there was a lot of things and a lot of details to pay attention to. So when it comes to details, a lot of times the best thing to make sure that you're paying attention to those details is to practice doing so. So today's aim is really more about practicing some things that we've just learned. And so I'm going to quickly run through about 4 problems, and then we're going to have some time that we're going to practice in an organized fashion. Okay? So first thing we're going to do, we're going to look at these 2 distribution problems. Each of these problems has a specific point to it, things that you can be writing down as your key points. Looking at this particular problem, this first problem I put on here because it seems like some of us are so used to distributions that only have 2 things to distribute to. When we look at a problem like this, sometimes we forget to distribute to all 3 things. And that's really the point here. We have to distribute to everything inside the parentheses. Not just one thing, not just 2 things, everything. Negative 2 times 2x, that's a bad date. Negative 4x. Negative 2 times 4 is negative 8. And negative 2 times 2y is negative 4y. Here we have this particular work, but this is not a completely simplified answer. Remember, when I'm talking about a completely simplified answer, I'm also going to ask you to switch any of these additions of negatives to a subtraction. So I'm going to change that and switch that, change that and switch that. Negative 4x, change to a subtraction, switch to a positive 8, change to a subtraction, switch to a positive 4y. So there are really 2 key points that you could have pulled from me doing this problem, 2 things I really wanted you to focus in on. Somebody with a raised hand, can you name one of the 2 things that I really wanted you to focus in on, why I redid this problem today, Jadea? Okay, leave, change, switch, additions of negatives at the end. That's one key point that you could be writing down right now. What's the other one, Kevin?
Distribute to all 3 of them?
Yeah, distribute to everything inside the parentheses. So if you're looking at your key points for today, I would suggest that you can go ahead and write those 2 things down. In fact, I'm going to do that now. At the end, leave, change, switch, adding of negatives to subtractions, and always distribute to everything inside. Okay. So this next problem also has a really important detail in it. We see that same thing about needing to distribute to all things, but the other thing that we recognize here is that we need to make sure that we get these coefficients in there when they are hidden. But most importantly is a step of work that I feel like a lot of you are missing. So when I distribute to all 3 things, remember I said on Friday, with this particular problem, we are distributing in a variable. Okay, so there's a variable here that needs to be distributed in. And a lot of you are skipping this particular piece of work. When we distribute a variable, I said you must absolutely show me the multiplications that you're distributing in. So this first distribution is negative 1x times 1x. And you should write negative 1x times 1x. Plus a negative 1x times a 3. Negative 1x times 2y is our final distribution. Oop, not plus, times 2y. Now, when we do these multiplications, this is very important. This is the other piece of this that I think is so important that a lot of us are just not paying attention to. When I multiply this, I multiply the -1 times the 1. That gives me -1. And I have to recognize I have two variables here being multiplied, x times x. There's a special way we write x times x, which is what, Kyrie? X squared. Plus, on this side, I multiply the coefficients, -1 times 3, which is -3. And the variables, I only have one variable here, so that's just going to stay x. Over here, we have -1 times 2 for our coefficients. -2. And I have two variables here, x times y. I can't combine those into an exponent, so I'm just going to rewrite that as xy. I would want to go ahead and combine like terms, but there are no like terms to combine, so I'm going to change switch these back to subtractions. Also, as I'm change switching these back to subtractions, I notice that, in this first term I write it down as -1x squared. Is there anything in that first term that we actually don't need to be there? Andrea? Yeah, the number 1. Whenever we have those coefficients of 1, we can just get rid of them. The negative has to stay, so we know that's -x squared, but the coefficients of 1 go away. Okay, there were a couple of key points we could have pulled from this particular problem. What key points do you think I was really trying to focus in on with this problem? Kyrie? So, when distributing variables, show multiplications for variable distributions. And what other key point do you think I was trying to get across with that problem, Andrea? Yep. At end, remove coefficients of 1. So those are the key points for those particular problems. We're going to move on to one that really just starts trying to combine all of the ideas that we already know. So we're going to go ahead and start with a leaf change switch here. Carson. And then we're going to focus in on our distribution here. We actually only have one distribution here. It's stuck in the middle, so everything else is going to come down. Make sure that you're paying attention to what the distribution actually is. A lot of people will distribute to things that are not inside the set of parentheses. So you just need to be very careful with that. Now I can associate and combine my like terms. 3x plus 12x is 15x. -15 plus -12 is -27. Change switch. We end up with 15x minus 27. Questions about that? All right, one last problem. This is the most complicated problem. Puts together a lot of the ideas, kind of a confluence of all of the ideas we've learned over the past 2 days. Start with a leaf change switch here. I also notice a couple of missing coefficients. So I'm going to fill in those coefficients, a leaf change switch, and a leaf change switch. So a lot going on here. I've got two distributions to do. Carson, both of these distributions are variable distributions. which means I need to show that extra step of the multiplication. That was one of our key points we wrote down. So with this first distribution, I have 3x times 1x plus a 3x times 2. Here after this leaf change switch, I'm distributing a negative 2x times 2. And I'm also distributing the negative 2x times negative 1x. The 3x and the negative 5x squared are not part of distributions. They're just going to wait their turn so they can be combined with other like terms later. Now I'm going to go ahead and do these multiplications. Thinking about the multiplications, multiply the coefficients. 3 times 1 is 3. X times x is x squared. 3x times 2, so that's 3 times 2 is 6. The x has nothing to multiply with. Negative 2 times 2, that's negative 4. X has nothing to multiply with. Over here, negative 2 times negative 1, that's positive 2. That's a good date. X times x, x squared. Here we had the 3x and the 5x, negative 5x squared, that are just waiting patiently. Now we're going to commute all of our like terms next to each other. I'm going to commute all of my x squared terms to the front because they are the highest order. Notice I'm marking them out as I go. This is a good strategy. I noticed when I did this problem the first time today that I hadn't marked out the 2x squared, and so I knew that I had not commuted that. So all we've done here is commute our like terms. Now I noticed that within my like terms, I have 3 sets within my like terms, which means I can only add 2 of them at once. So I'm going to use the associative property. I'm going to add 3x plus 2x squared first. That gives me 5x squared plus negative 5x squared. I'm going to add my 6x plus my negative 4x. That's going to give me 2x plus the 3x we have over here. So now I want to finish combining my like terms. I have x squareds plus x squareds, 5x squared plus negative 5x squared. It's 0. Those are inverse operations. They add up to 0. That's like 0 times x squared, which is 0. So this is 0 plus 2x plus 3x. That's 5x. 0 plus 5x, that's the additive identity property. That's just 5x. And this should be an excellent reminder as to why we use simplification and why scientists would use simplification. They might have an equation like this that they've created, and then they're going to end up plugging into this equation 15, 20, 30, 100 different times with 100 different x's, and it would be 5 minutes per problem every time they plugged in an x up here, or like 2 seconds plugging in an x down here. Because this is easy. 5 times 2, 10. 5 times 3, 15. Or up here it's 3 times 2 is 6, plus 2 plus 2 is 4, 6 times 4, that one's 24, plus negative 2x, that's negative 4, blah, and my brain's going to get fried just trying to do it, right? It would take a long time. That's why we use simplification in the real world. Any questions about our work for today? Awesome.